We're going to talk a little bit about how we hear and go into the decibel scale some, which is something all of you need to know a little bit about because the decibel scale, knowing it and knowing something about it, is one of the ways you're going to help keep yourself from messing up your ears. Right? So this is a bit of a safety thing as well as talking about physics and how the ears work. Um, so sound is nothing other than the movement of air, and the movement, when you're hearing sound, the air is moving in waves, not up and down like water waves, but back and forth. All right, back and forth with little compressions where the air kind of squeezes together, like when you squeeze a spring together, and then as it releases, you get what we're calling here a rarefaction when the air gets thinner right behind the compression. These waves come into your ear, they hit your eardrum, and that force propagates then to the rest of the ear as the sound waves make your eardrum go back and forth. One of the reasons that listening to really loud sounds is bad for you is it comes in here, your eardrum is there to try and keep things on that side. The pressure stays out here in the ear canal. But your eardrum is flexible. But if you flex it too much, if you listen to really loud music too much, then the eardrum can slowly develop a little scar tissue and it becomes less flexible. As it becomes less flexible, your ability to hear goes down. This is essentially what happens in the aging process. As you age, your eardrum becomes less flexible. As it becomes less flexible, people have to shout louder and louder and louder for you to hear them, or you have to go get a hearing aid. And if you get a hearing aid and you wear your hearing aid, please turn it on. Don't turn it off like my father-in-law so that people think you can hear them or they can hear you or you can hear them but you can't, right? Turn it on. Um, Now, what happens in the ear? The eardrum moves these little bones right here. As the eardrum goes back and forth, it moves these little bones. These little bones hit a little window right there, a little oval window. The oval window causes the fluid in the cochlear to go back and forth at the same frequency that the sound is going back and forth. You end up with fluid going back and forth in this little pardon me spiral um, spiral organ right here, the cochlear. That little spiral has in it lots and lots and lots and lots of little hairs. Now here's the thing. Each piece of this, it's kind of like a piano. Each piece of this is responsible for a different note. So one of the things that often happens in hearing that we had to actually start making adjustments for with safety gear is if you're, say, working in a computer server room where there's the 3000 hertz hum of all the computer fans, that means a little piece of this that is responsible for 3000 hertz can get worn out and you'll simply stop being able to hear that frequency. Right? So one of the things that you're looking for in trying to protect your hearing is making sure you're not listening to a constant frequency all the time, because that's going to wear out the piece of this organ that's responsible for receiving that sound. And you don't want things to be too loud because that's going to wear out your eardrum faster. Another thing that happens when you have a cold is this eustachian tube will get clogged, and when the eustachian tube gets clogged, pressure can build up behind the eardrum. You don't hear as well then because the eardrum can't flex as much as it should because of the pressure behind it, and it can hurt. The other bits of the ear, these little canals up here, they're responsible for your balance. So they're little loops, and they have ionic fluid in them, charged fluid in them, that moves around as you move around and kind of tells you where you are in the world. And then, of course, there's the nerve going on off from the ear. The speed of sound is one of those pieces that we're um, always going to be concerned about, because the speed of sound is not a constant, unlike the speed of light, which is a constant. The speed of sound in air depends on temperature. So the speed of sound in air is 331 meters per second plus 0.6 meters per second per degree C times the temperature in degrees C. So at freezing, which is 0 degrees C, the speed of sound is 331 meters per second. 331 meters is about 1 1/3 football fields. And so if you think about this, if you count, if you like see lightning strike off in the distance, and you count how long it takes for the lightning to get to you, if the lightning takes 3 Mississippis to get to you, then it is about 1 kilometer away, because 3 seconds gives you about 1 kilometer at the speed of sound in air. The other thing about the speed of sound and wavelength and frequency is there's a constant relationship between the speed of sound, the wavelength, and the frequency. So very often the speed of sound, well, the speed of sound is a constant for all frequencies, so they all have different wavelengths to get to lambda, which is the wavelength, times f, which is the frequency, equal to v of the wave, velocity of the wave, or the speed of sound. The other thing we worry about is intensity of the wave, and the scale we use for that is the decibel scale. This decibel scale was developed by Alexander Graham Bell, and what it reflects is the fact that our hearing is not linear. In fact, our hearing, our response to intensity, is logarithmic. So there is the formula for calculating decibels is this one. Your intensity in decibels is 10 times the log, and that's a base 10 logarithm, of the intensity of the sound divided by this reference intensity, which is 10 to the minus 12 watts per square meter. This reference intensity is the softest sound that most people can hear. And so we're taking it with respect to that reference. I'll give you a slightly easier form in the discussion to look at in terms of this equation, but this is what decibel defined as the intensity scale. And the intensity is basically how much power per square meter sound has in it. All right. What's the one thing about this scale is that you don't when you double the intensity, that doesn't double the decibels. Why? Because it doesn't appear to be twice as loud to us. And that's one of the things and this is one of the things Bell captured with his formula, that the appearance of the intensity to us is different from just a linear progression in intensity. Other things that you're familiar with already that happen with sound is if something is moving towards you, its frequency goes up, or if it's moving away from you, its frequency goes down. So you know this from an ambulance passing you. It's going wah 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 wah, and we can actually calculate that using the Doppler equation that we have right here. Right? And this is happening because as the sound is moving towards you, this thing making the sound is also moving towards you, and that decreases the space between the wave fronts, making the frequency go up. All right? And on the other hand, when it's moving away from you, if you're this guy over here and you're moving away from you, the thing making the sound is moving away from you, which is increasing the spacing in the wave fronts, which means that the frequency is going down. We can also worry about this in terms of if you're moving towards something that's making noise, the frequency goes up, or if you're moving away from something, the frequency goes down. We're not going to worry about this piece so much, but it's slightly different form of the equation. We're going to worry about this one, where you have your wave velocity divided by your wave velocity plus or minus the velocity of the source times the frequency the source is putting out. That gives you your observed frequency. Now, if the source is moving towards you, use the minus sign. If the source is moving away from you, you use the plus sign. That's why there's the plus or minus there. The other thing with sound that you've heard of before is a sonic boom. And a sonic boom occurs when an object is moving faster than the speed of sound. That means there's this cone in which all the sound is arriving at the same time. And so as that cone passes by you, you hear the sound from all of the track along which the object is moving, and it makes it a big boom, therefore the sonic boom. Okay, quick review on what equations we'll play with. We're going to play with the velocity equals wavelength times frequency, and we're going to play with, pardon me, the velocity is 331 meters per second plus 0.6 meters per second degrees C times the temperature in Celsius. We're also going to play with the decibel scale. Beta is 10 log your intensity over this reference intensity, 10 to the minus 12 watts per square meter. And we're going to play with the observed frequency is your frequency times the velocity of sound divided by the velocity of sound plus or minus the velocity of the source, right? Frequency of the source, velocity of the source. Use the minus if the source is headed towards you. Use the plus if the source is headed away from you. Okay, that's it for our lecture on sound, and I look forward to your comments.